We began our discussion of analog electronics with the resistor. And it's the simplest component in our toolkit. Allows us to do voltage division and some useful things. But now we need something that gives us a little more power. So now we need our next most simple electrical component. And that's the capacitor. So a capacitor plus a resistor gives us a lot of interesting things we can do. And it's critical that we understand how they're different. Because what we typically want to know about new components is their current voltage relationship. We're going to be driving in that direction. Remember, for the resistor, that was Ohm's law, V equals IR. Capacitors are a different component, so there's going to be a different current voltage relationship. And it's going to take us a couple more steps to get there. The structure of a capacitor is two metal plates with a gap between them. It can be vacuum, it can be some insulator. The key idea is that electricity cannot move across this gap. And that would seem like we've made an open circuit. And to some extent we have, but it's a very special open circuit. And we'll see that in some sense we can't get electricity across this, but in a very important sense we can, and that's what we're trying to learn. So the basic physics here is that when we put a voltage on this element, it's a two-terminal device, we can put it in a power supply across it, and we can put a voltage on it. When we do that, we might drive a bunch of charge onto one of these plates. So I'm just going to label some positive charge. That's being pushed in, and it can't get across, so it piles up on the plate. And this is, similar, if you will, to static electricity if we're doing this all relatively slowly. If we had a small positive test charge and we brought it near that plate, we'd feel a repulsive force, like charges repel, remember. So what happens is, remember what makes metals metals, what makes them conductors, is there is charge that can move around. That's why we can do the experiment we just did there. And when we do that, it's going to drive positive charge out that way, such that we end up with this plate being overall negatively charged. So the key idea is we drove some positive charge in, and the same amount of positive charge came out. It just wasn't the same positive charge. It was simply the same amount. There's a gap in the middle that the charge cannot get across. The force is what can get across. The electrostatic force that's attracting these negative charges, or if you will, repelling these positive charges that ran away. So what this means then, in terms of using the device, is if we put a static DC, constant voltage across here, and maybe we turn that power supply on, we might see a little blip of charge come out, a small amount of current for a small amount of time as these plates charge up. But then it will stop because the plates will get charged up. No more current will flow through the device because we've charged it up. So the key is we can't get static, constant, direct current through a capacitor. And that it begs the question of, well, is there some other kind of current we can get across it? And we'll do that next.